an example and the Berufkus algorithm for finding the minimal spanning tree. This is the example at Wikipedia. It is a graph with 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 at 12 vertices. Initially, each vertex belongs to its own connected component. In each step, we try for in each iteration, we will find the edges that is shortest to the connected component. Since initially each vertex belongs to its own component, we will find the minimal edge for each that is in that or incident to the vertex. For A, there are 2 edges connected and 6 is smaller, so we choose the 6th edge. For B, there are 1, 2, 3 with the corresponding weight 1, 7, and 13. Since 1 is the smallest, we choose 1. For C, we find the edge with the minimal weight. Here, 28, 14, 7, 6. 6 is the minimum. For D, 1, 14, 9, 3. So 1 is the minimum. For E, 8, 18, 2, 9. 2 is the minimum. For F, 2 and 3, and 2 is the minimum. For G, 5, 10, 19, 15. 5 is the minimum. For H, 15, 20, 17, 17. So 15 is the minimum. I, there are 5 and 11, and 5 is the minimum. J, 18, 17, 19, 16, 4. So 4 is the minimum. For K, 11, 10, 16, 12. So 10 is the minimum. For L, 4 and 12. So 4 is the minimum. After finding out the minimal edge for each connected component, then we join the connected component to form a larger connect. We join the connected component in and merge them components into and merge them into a like a super vertex, or you can just call it a larger connected component. So here the only difference is that we highlight the connected component by the same color here. So after merging, initially there are 12 connected components, and now it is reduced to 1, 2, 3, 4, 5. 5 connected components. Likewise, we want to find out the minimum edge that is incident to the connected component. So for the green light connecting component, there are 13, 7, 14, 8, and 20. So 7 clearly is the minimum. The second connecting component, the yellow one, we have 13, 7, 14, 9, and 3. So 3 is the minimum. For the light blue one, there are 3, 9, 8, 18. So 3 is the minimum. For the red one, the red connected component, they are 20, 17, 19, 16, 12, 11. Oh no, this not. Uh, Again, 11 is not included. Again, 20, 17, okay, 19, 16, 12. So 12 is the minimum. For the dark blue connected component, we have 12, 16, 19, 17, and 18. So 12 is the minimum. So again, we merge the connected component into a larger connected component, or you can call it a superset. And after merging, the 5 connected components be, became 2 connected, a larger two larger connected components. And again, we examine the vertex connecting these 2 connected components. They are 20 and 18, and clearly 18 is smaller. So at last we merge the 2 connected components to form a minimum spanning tree. The algorithm in each iteration, for a large part that in each iteration the number of connected components can approximately cut in half. Right? That at first we have 12 connected components, and the second time we have 5 connected components, so 12 to 5, and at last we have 2 and 1. So for each we will have logarithm. The complexity should let me think. The complexity should be log v, where v is the number of v is the set of vertices in the graph. Okay. This is for each iteration, and no, we will have log v iteration, right? Log v iteration, because we cut in half the number of vertices each iteration, and for each iteration, at first we will need to examine or iterate through all the vertices. In the example, it looks simple because we only need to find out the vertex between 2 different connected components, but in the worst case we need to examine all the vertices. So for each iteration, we may need to examine all the vertices. So the complexity is the number of edges. So the total complexity with our rigorous proof is number of edges. This is the time complexity for each iteration, and we have log v iterations. Okay.